problem in that harmonic motion. So this is example 4. So I copy it here. The application problem that you did in the homework is spring mass system mostly, and it is set to the equilibrium position, the height to be 0. Okay, so here's a slightly different situation. It's a modeling brightness of a variable star, and I use the following technique in my class, calculus class as well. Mass attached to spring system, you see that object and you see this is moving. What they're talking about here is the brightness of a variable star. It is not something, the object that is moving in front of you. But think about the situation, there's some equipment that measures this brightness and indicates the brightness using as a horizontal bar. So just focus on that, for example, end of the horizontal bar, just like temperature, thermometer, and things like that. And the velocity, everybody understands. Sometimes people don't understand quite the acceleration. But since when you're driving, you have this needle in the speedometer, and how fast the needle is moving is definitely, it's a motion of a needle is actually the acceleration. So this abstract kind of idea and a quantity visualized as a dot or at the end of the vertical bar that often is used to indicate in a digital device. So as this you go move around the sun, or as is observed, and this brightness changes and this dot is going up and down. That's a motion. Sometimes the brighter, so it go up here and hitting the highest, the brightest spot, and that dot is going down and somewhere here hitting the lowest spot. So that's the situation. Although it's a brightness, if you can imagine that there's a equipment, and you can turn that brightness into a motion of the dot, and then it becomes the same thing as a mass attached to a spring system. It's not easy to understand why this follows harmonic motion. It's just that going up and down, that's all it can figure it out. Another situation is that maybe there is some star, and here's a planet. It's moving around like this, and we're here as an observer from a far distance. It's called a Duffel Effect, that at that point is kind of moving toward to the observer, so it shows a brighter brightness of that star, just like a honking truck is approaching you, and then as soon as it passes you when you're standing by, that sound is kind of fading away, right? You have that experience. That's called Duffel Effect. That happens to all the wave observation. So when it is moving away from the observer at that stage, maybe it's less bright. At that stage, it's brighter. And you don't really see the motion from a far distance, but you see the phenomenon of sometimes it's brighter, sometimes not so bright, and it is kind of explained from what we understand how the motion works and things like that. Here's a circular motion. Maybe you can analyze it further, relate it back to somewhat sine and cosine, and conclude this must be the harmonic motion. If not exact, somewhat it must resemble harmonic motion, things like that. Alright, so we're going to just assume this is a harmonic motion and try to fit into the sine and cosine curve. Another thing is that this equilibrium position is not set to 0. Okay, let's read it here. The star is brightness is alternately increase and decrease, whatever the name of the star is. Time between the period of maximum brightness is a 5.4 days. Although they use the word periods, you have to clearly understand what period they are talking about, whether it coincides with the way we understand the periods of a sine and cosine curve. But if you further read here, the average brightness or magnitude of the star is a 4.0, whatever the unit is. So how do you understand this number 4.0 in terms of amplitude line, period, and frequency? What is a good word that describe this? So that's right in the middle position, right? That's in the gauge. Right next to it, it says 4 right next to it. What was the standard name for our sine and cosine curve or harmonic motion? The position and right in the middle, kind of average, was equilibrium position, right? So that corresponds to middle equilibrium position. Most of us, A times sine omega t. If you write it just like that, y equals omega t. This one is the equilibrium position where? So y equals 0, right? Going up by a units and going down by a units, things like that. So this one has a shape like this, right? That's the sine curve. The middle position right here is called the equilibrium position. Think about mass attached to spring, going down and coming back to middle position and go compressed and come back and things like that. That was called equilibrium position. So our interpretation of this average brightness is the equilibrium position. Okay? This one is the equilibrium position 0, right? And how do you change that? Well, you can actually go and reset this one to 0. That would be convenient, but let's respect that. It's brightness 4 is just brightness 4. All right? If the equilibrium position is above and at 4, what do we do to this function to match that equilibrium position? Do we multiply 4 or shift 4? Shifting is the correct one. It's a 4 plus a times the sine omega t. Okay? That's our interpretation of the average brightness. Okay. And also its brightness varies by plus minus 0.35 magnitude. So here's a 4, that's the average. So it's the top position here. What is the maximum magnitude they're talking about here? It varies, plus 0.35 and minus 0.35. So that one would be 4.35. It goes up to that. What about bottom here? 3.65. That goes below by 6.5, 0.35. Does that make sense? So the graph is going to look like this. What is a good vertical axis? Brightness, B, that's what we're measuring, right? It's like there's this dot moving up and down, just like a motion of a dot representing the brightness. And here's a time axis t, right? What are the time unit they gave us is days, right? So maybe here's the days, in days. And there's no 0 date. It's kind of periodic because it's circle around here like that. So it's a matter of where you set this thing. Okay, we're going to set it to a minimum brightness state. Let's start it from there. Maybe we're going to set the 0 day at the maximum brightness. Maybe we're going to set it to whenever it's average date, things like that. It's your choice. But from what is described in here, between periods of a maximum brightness. So why don't we stick to the maximum? One day you weighted it, and then it reached the maximum brightness. Then you set that as a 0 day. Is that okay? It's all times relative. So 0 day, what is the maximum brightness then? 4.35. So here is a 4.35, right? And that's going to be the maximum. Think about the red dot here in the gauge is moving up and down. The highest position it's going to hit is that one, right? What is the lowest position it's going to hit? So compared to this being a 4.35 unit, 3.65 unit is kind of above here. It's not quite accurate, but is that okay? So that's going to be 3.65. Did you have a question, Ashley? No? So that's it. So where does this start? Does it start at the top amplitude, bottom amplitude, or equilibrium line? Does anybody remember what this equilibrium line is? 4. That's right. This is where B equals 4. That's the average. Go up higher, it's the brightness. Where does this start? In the 0. It doesn't say we set it to a certain way. We set it to be the highest brightness, right? And then it began to go down and hit the lowest spot and coming back up. Is that okay? So that would be time period between maximum brightness. Was the maximum brightness, it came back to the maximum brightness. This dot moving up and down like that. That coincides with our notion of one cycle motion of this red dot in this gauge, right? So what is this length here? 5.4 days. And what kind of curve is that? Sine curve or cosine curve? is a cosine curve. Is there reflection involved? Yeah. So it's a cosine. Cosine is the x coordinate of the unit circle when t equals 0. What is the x coordinate? T equals 0. Find the angle 0 on the unit circle. On the unit circle, not inside. Is 1, right? So we start at the top. Cosine starts at the top. Reflection, you start at the bottom. Sine starts at the equilibrium position. Reflected, you're heading going down. Usual curve is going up. Okay? All right. So we know it's actually in what kind of shade? Y equals shift, right? Shift 4. Remember that shift business? Because equilibrium position is 4 now. Plus a times, we know, is a cosine curve. And there's omega there and t there. So if you can figure out a and omega by looking at this graph, and you're done. And that models the brightness of this star they're talking about. Okay? So why don't I make this part exercise and you figure out a being, make sure you think about a being positive or negative, right? Or what is the omega? How is it got to do, what information is relayed back to? Okay, that's the exercise. Exercise there is compute a and omega, and this is supposed to be b, the brightness, b here, and find a function, and compute to b. It's the easier way to write it. Is that all right? That was a key. That period that we observed there is supposed to be 2 pi over omega, where omega is the coefficient that is in the formula. And a being amplitude, that part's all right? Go up and down, and that's the amount. No reflection. That for that we choose this positive sign there. Okay, any question? That's the end of kind of application of two sides. The geometry side, we looked at law of sine and law of cosine, and this motion side, we redefine this function, a function of time, and model this type of harmonic motion. It has